Test. Alright. Looks like we're hello. Test. Okay. Looks like we're good, I think. Hmm. But sometimes, yeah, the voice doesn't pick up sometimes. Maybe it's because, hold on, blah 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 blah. Test. There's such a delay. Hold on. Can I reduce the delay? Hello. Ba ba ba. Yeah, mic isn't getting picked up. I think maybe if I just close this and like open it again, we'll get test blah blah blah. Because yeah, there is test. Okay. Blah da. Let's make it a bit lower than like that. So even if I'm talking quietly, it still gets picked up. Let me try whispering. Okay. Alright, that cutoff seems low enough then. Cool. Right, so what are we doing? We're gonna continue. I think the last time I touched on this was like a month ago or something. So hopefully, I mean, I did like gave the book a little bit of a skim so that we can remind ourselves about what we did last month. And we can move on to Unit 2. Right. The text Go and number 28487 are both represented with the same number of zeros and ones on an x86 computer. Okay, the type establishes what those bits and bytes mean. One is a string of 2 characters, the other is a 16-bit integer. The string type is used for multilingual text, and 16-bit integers are one of many numeric types. Unit 2 covers the primitive types that Go provides for text, characters, numbers, and other simple values. When appropriate, these lessons reveal the benefits and drawbacks to help you select the most appropriate type. Lesson 6. Real numbers. After reading Lesson 6, you'll be able to use 2 types of real numbers, understand the memory versus precision trade-off, work around rounding errors in your piggy bank. Computers store and manipulate real numbers like 3.1415.9 using the IEEE 754 floating point standard. Floating point numbers can be very large or incredibly small. Think galaxies and atoms. With such versatility, programming languages like JavaScript and Lua get by using floating point numbers exclusively. Computers also support integers for whole numbers, the subject of the next lesson. Consider this. Imagine a carnival game with 3 cups. The nearest cup is worth 0.1 to 1. The next is worth 1 to 10, and the farthest cup is worth 10 to 100. Choose one cup and toss as many as 10 coins. If landing 4 coins in the middle cup is worth $4, how would you win $100? What? If landing 4 coins in the middle cup is worth $4, so 1 coin is $1, how would you win $100? You toss into the furthest cup once? I don't know. No, you can't do it. Wait, I don't understand what the point this is trying to make. To represent many possible real numbers with a fixed amount of space floating. Oh, it's like it's like the decimal, no, base system. So like, this is talking about base, like base 10 with the decimal bases included as well. So basically, if you put like 5, 6, 7, then that translates to 75.6. So you're just sorting stuff into these cups, and each cup has like a maximum of 10 number of coins that you can put into, and if you put like more than 10, then that gets like transferred over to the next cup, and so on and so forth, which is how bases work. And in computers, that would be like base 2, right? So to represent many real numbers with a fixed amount of space, a floating point number is like choosing one of 2048 cups and placing anywhere from 1 to several trillion coins in it. Some bits represent a cup or bucket, and other bits represent the coins or offset within that bucket. One cup may represent very tiny numbers and another represent huge numbers. Though every cup fits the same number of coins, some cups represent a smaller range of numbers more precisely than others, which represent a larger range of numbers with less precision. Every variable has a type. When you declare and initialize a variable with a real number, you're using floating point type. The following 3 lines of codes are equivalent. So yeah. Yep, it'll automatically know that if you just put this in, then it'll automatically know that you're using the float 64 type, because this is a decimal number. So yeah, it's valuable to know that days has a float 64 type, but it's superfluous to specify float 64. Yep, that's exactly just what I said. The Golang tool provides hints for coding style. It discourages the clutter with the following message. So that's the whatever thing is in my VS Code. The Golang. Do I have a Golang? I don't know. Yeah, we can test if we have Golang or not by typing in, let's say here, I guess, var days float 64 equals 365 point blah blah blah. Oh well, that's not the right spelling for float. Yeah, I don't get that specific sort of message, so I don't think I have Golang installed specifically. So yeah, tools I have Go PLS, Go Tests, IMPL, Go Play. Oh, they're all not installed apparently. Well, whatever. Okay. We don't really need that. So, okay. If you initialize a variable with a whole number, Go won't know you want floating point unless you explicitly specify a floating point type. Okay, single precision floating point numbers. Go has two floating point types, float 64 and float 32, which is less precision. I have math.py, which is probably from the math package, right? So yeah, if we just copy all of this, so we're saying that the variable pi64 be math.py, and math.py is this value. Yeah, you can see it over here. Wow, okay. And it sees this value and it's like, right, I'll just assign it the type int, no, not int, float64, right? And because it's float64, I assume, um, has enough precision to store all of these numbers here. But then, if you do the same thing, but then you add an additional instruction here that says, I want you to view pi32 as a 32-bit float, then it's going to cut off some of the decimal points here in order for it to be properly interpreted as a 32-bit float. So let's just see that in action, I guess. Go run unit2.go. Oopsie daisy. I guess we just do ln, and then we don't need to print the new line explicitly. So yeah, there it is. In Go, each type has a default type called a zero value. The default applies when you declare a variable, but don't initialize it with a value. So if I just declare something ASD, but I have to give it the type, so float 64. I guess we declare it, but then we don't specify what it should be. Then there's a default value, and that should just be the number 0. Yeah. Okay. Okay. Let's remove all of this and try this piece of code out. 1 divided by 3 third. We'll just print ln third. Oh yeah. So that's interesting that it still decides to print 0. Um, because I think I know why. So 1 is seen as an integer and 3 is seen as an integer. So if it takes the division, you're dividing two integers and the division of two integers. Well, in sort of computers, they usually have their own division for natural numbers, which just rounds down so that the division takes two natural numbers and outputs, well, not necessarily natural numbers, just integers in general. So two integers, and then that outputs another integer, and it does this by rounding things either down or up. Or we can check. We can put 2 in here, and just run this again, and see that it still becomes 0, so it basically rounds down. So if we do 4 divided by 3, for example, then we should get 1. Yep, because it rounds down. So we can just test this again. 4 out of 100 should be 0, but then if we have 103, that rounds down to like 1, so we get 1, and then 199, even though it's very close to 2, should still round down to 1, because that's just how the division between two whole numbers is defined. It should always return a whole number. But if you do 1.0, now it's reading this and it says, okay, this is not an integer, not a whole number. This is a float. So when it reads this division, it's like I should use the float type of division, not the whole number type of division. And then so you have a float and then a division that is the float type of division, and you have another number here, which normally it would be read as an integer or a whole number, but then you have all of these other contexts, which makes this 3 get interpreted as a float as well, which means that the entire thing just evaluates to a term with the float type, so that we get a float in the end. Cool. So this basically just says that we can specify the number of decimal points that we want to print out. So so we do percent dot, so percent dot 3f, and then just third. It has to be in quotation. Right, so this specifies the number of decimal points we want. What I'm confused about is what this 4 is doing. So the 2 specifies the 2 decimal places we want, but I guess it shows it over here. So that's width and precision, although I don't really know what. Oh, width. Okay, so a width of 4. What does a width of 4 mean exactly? What happens if we increase the width to 10, let's say? What exactly does the width do? It's just some extra space here. So if do, what about a width of 1? That does nothing. Because we have 1, 2, 3, 4 characters. So it only makes sense to do like 4 and above. Minimum number of characters to display. Including the decimal points and digits before and after the decimal. It's the minimum number of characters to display, but if we put in 1, you're still displaying 4 characters. So that doesn't really work, does it? Width specifies the minimum number of characters to display, the lowest number of characters to display, in other words. So if the minimum is 1, oh, minimum is 1, not maximum. Right. So, okay. I kind of get what it means now. Right, so this basically means I want a minimum of 5 characters, and I want any extra character to be represented by a 0 on the left. So when we do this, basically it'll try to print 0.33, and that takes up 4 characters. And so this guy over here says, nope, you need 1 more, and it has to be a 0 on the left if you are going to need an extra one, which you do need because 0.33 is 4 characters. So you add 1 more to reach the minimum requirement, and then you get 0.33. Okay. So can you put any number here, like 2? Or will that get interpreted as a minimum of 25? Yeah. So I can't put 2 and then replace this with a 2, for example. Right. Okay. Let's keep going. Floating point accuracy. Right? We all know about this. Sort of. Okay. So over here we divide by 5 and multiply by 9. Which is the same thing as 9 divided by 5 multiplied by Celsius plus 32. But then if you multiply first, so this is Celsius times 9, and then you divide by 5, and that's more accurate. Okay. Okay. So the absolute value just takes the distance. So piggy bank, the distance between piggy bank and 0.3 is less than 0.0001. Okay. If you add 11 dimes, you don't get 1.1 cents. Mhm. Alright, so mini exercise here. Save some money. You save some money to buy a gift for your friend. Write a program that randomly places nickels, dimes, and quarters into an empty piggy bank until it contains at least $20. Display the running balance of each piggy bank after each deposit, formatting it with an appropriate width and precision. Huh. Okay. Let's try that out, I guess. So let's see. So we have funk. Wait, no, it'll be outside of main. Have funk coin, and coin will be, I guess, a float 64, and I'm just copying stuff here. Value. Okay. Var value float 64. So our value will be either a nickel, a dime, or a quarter. Or actually, we could um okay, since we're making a program that prints stuff, it would be helpful to no, not jeez, what am I doing? Text. So we have nickel, dime, quarter. And we just return text. right? And get dime, 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 quarter, quarter, nickel, nickel. Cool. So we have something that randomly generates a coin, and then now we want something that gives us the value of a coin. So we have a coin here. And this gives us a float 64. So we have, yeah, a variable called value, which is a float 64. And then we switch coin. And we have case nickel value should be 0.05. And then we'll just repeat this with dime and quarter. So dime is 0.1, quarter is 0.25. So you have a coin, so we can print the coin out, and then we can print the value of that coin. Right, we have to return return value. Okay. Undefined coin. Excuse me? What? Do I have to say string here? Okay, cool. So I have something that randomly generates a coin, and we have a function that gives us the value of the coin. Cool. So I have, I guess, something called a total. So our total will start at 0. Let's do that to ensure that it gets read as a float 64. And we want to do a loop. How do we do a loop again? So we do a for, and then we want total to be, so this is the condition for it to like still be going, right? So as long as count is above 0, keep doing this. So in our case, as long as our total is below 20, right, below 20, keep doing this. Right, and then we just have to close this. So first, let's generate a coin, a random coin, with our function. and then we want to get the value of that coin. So we just have to do that. Now we want to do fmt.print. Hmm. Okay. Let's try this. This is a very minimal example, but oops, what's going on here? Wow, okay. That's totally not what I anticipated. Wait, let's do a dash n there to make things cleaner. Still didn't make things cleaner. Wait, you do? Oh, it's the wrong dash. So I don't know why, but it's not printing things correctly. And that's because I've kind of forgot how the print actually works. Do we do %v? Yes, we do. Okay. So we have a record of so we added a dime, so our total goes to 0.1. Add another dime, the total goes to 0.2, and so on, and it keeps going until we hit that, whatever. So basically we could simplify this by doing, if I remember correctly, percent f dot um dot 2, right? Because we only ever need 2 decimal places. That did not work at all. So how do we do the decimal place thing again? So percent. Oh, you do the number first and then F. Okay. Wait, no, we don't. Wait, what? Oh, we do percent F instead of percent V. Okay, so percent. Um. So something like that. Okay, cool. Alright, I'm gonna go to the toilet, and then we're going to just clean this up, I guess. Okay, I'm back. So we could say added, added, and then the coin. Guess we should make this lowercase. And we could say total is now, and we could add some padding, of course, to make things look better. How do paddings work again? So does something like that work? Nope. Totally ruined everything. Um, but I still don't understand how padding works. Uh, Go program. I want this padded nicely. Okay, this is nice enough, I feel. Yep. Okay. This is okay. Yep. What do they call it? Piggy.go. Piggy.go. Okay. Let's go to lesson 7, whole numbers. We have lesson 8, big numbers, lesson 9, multilingual text, converting between types, and we have our capstone, which we will try to do, maybe. Whole numbers, you'll be able to use 10 types of whole numbers. Choose the right type, use hexadecimal and binary representations. Go offers 10 different types for whole numbers collectively called integers. Integers don't suffer from the accuracy issues, but they can't store fractional numbers and they have limited range. Okay. Unsigned means only positive, okay. Oh, okay. That's interesting. So it looks like the year value variable and it prints it's the type of that variable. And then you have to include the year again because you want to actually print the variable instead of just its type. Oh, okay. Hexadecimal. Okay. Mm-hmm. To distinguish between decimal and hexadecimal, Go fixes requires a 0x prefix for hexadecimal. These 2 lines of codes are equivalent. Mm. Mm-hmm. Mm-hmm. Uh, I see, I see. Okay. So let x be 2, 1, 2. So you can print f percent x x, and this should give us the number 212 in hexadecimal. Right, I forgot that we should do that. D4. Right, and 255 should be FF. Cool. Okay. Okay, and they just wrap around if you go over the limit. I think I understand all of this. Blah blah blah. Avoid wrapping around time. On Unix-based operating systems, time is represented as the number of seconds since January 1st, 1970. In the year 2038, the number of seconds since January 1, 1970 will exceed 2 billion, the capacity of an int32. Thankfully, int64 can support dates well beyond 2038. This is a situation where int32 or int simply won't do. Only the int64 and uint64 integer types are able to store numbers well beyond 2 billion on all platforms. The code in listing 7.5 uses the Unix function from the time package. It accepts two int64 parameters corresponding to the number of seconds and the number of nanoseconds since 1970. Nanoseconds. So 1, 2, 3 is 2 minutes and 3 seconds, so time is 2 minutes and 3 past midnight on this 1970 January 1st. Oh, okay. What if we add some things here on a millisecond? Ooh, interesting. I wonder if we can get how many seconds from the current date. Okay, that was a short lesson, which is nice. But I want to try something out. Um, just epoch. Yeah. Okay. So time dot no, it has to be capital. So time dot now just gives us the current time. BST. I don't know what the m equals whatever that is means. It has been that many seconds since 1970. So if you divide that by 60, we get the number of hours. If we divide that by 24, we get the number of days. If we divide that by 365, we should get the number of years, which should be like 50 something. That is not 50 something. Wait, seconds divided by 60 turns into minutes, and you have to divide by 60 again um, to get the number of hours. So it should be 50 something, 55, which is, yeah, 2025. So yeah. Okay. Pretty darn cool. So Unix. So time.unix. Oh, okay. So what does Unix do exactly? Wait, so do we just use Unix as a function and put X inside of it and have everything still work? Nope. Method call and the function calls. Oh, okay. It's a method instead of a function. Okay. Okay. Let's go to lesson 8. Big numbers. Goes big package for really big numbers. Computer programming is full of trade-offs, blah blah blah. Okay. If you haven't realized it yet, 64-bit integers are mind-bogglingly big, much bigger than their 32-bit counterparts. For some perspective, the nearest star, blah blah. Rather than painstakingly typing every zero, you can write such numbers in Go with an exponent like so. And int 32 int u int 32 can't contain such a large number, but an int 64 doesn't break a sweat. Now you can go about your business perhaps calculating how many days it would take to travel to Alpha Centauri, a task tackled in the following listing. Okay. As big as 64 integers are, there's something bigger. Space. The Andromeda Galaxy is 24 quintillion kilometers away. Even the largest unsigned integer, u int 64, can only contain numbers up to 18 quintillion. Attempting to declare a variable beyond 18 quintillion reports an overflow error. But don't panic, there's still a few options. You could use floating point math. That's not a bad idea, and you already know how floating point works, but there's another way. The next section takes a look at Go's big package. So big.int is for big integers. When 18 quintillion isn't enough, big.float is for arbitrary precision, floating point numbers. Big.rat is for fractions, like 1/3. Hmm. Methods are similar to functions. Yeah, that's what we saw before. You'll learn all about them in lesson 13. The new built-in function is for pointers, which are covered in lesson 26. So new, yeah. Okay. Hmm. Ugh. Okay. Constants of unusual size. Constants can be declared with a type just like variables, and just like variables, a in64 constant can't possibly contain a number like 24 quintillion. Okay? Gets interesting when you declare a constant without a type. For variables, Go uses type inference to determine blah blah, or flows in type. Constants are different. Rather than infer a type, constants can be untyped. The following line doesn't cause an overflow error. Also, constants are fine, but variables are not. Though the Go compiler utilizes the big package for untyped numeric constants, constants and big.int values aren't interchangeable. Listing 8.2 displayed big int containing 24 quintillion, but you can't display the distance constant due to an overflow error. Okay, lesson 9. This will be the final one. Nope. Yeah, and then there's lesson 10, and then there's the capstone. Right. String literals may contain escape sequences, such as \n. Backticks indicate a raw string literal. Right. So you can just, okay. Interesting. Byte and rune. So let's try it out. We could have the, was it %C. So I want to print let's say the number 23 as a as a um as a character, and that does not work. So it has to be a variable. So I'll say test equals 23. That also doesn't work. Oh, not print ln, print f. That produced nothing. Wait, what if I just... Still nothing. 960? Put 960 in here. Ooh, okay. So it does work. Just not all numbers work, I guess. The fuck is this? I got a random kanji. Not even a kanji. This is like probably... Yeah, it's not showing up in my dictionary. But yeah, lots of Chinese characters are basically just like not used at all. 中国哲学、哲学、哲学。中国哲学、電子化、計画、計画。Let's try... Let's try this. So... Okay, so we have Unicode, right? So we have U plus 2248. So if you put 2248 in here, that is not the same thing as this. We actually have to download stuff. Can't we just see... Yeah, like that. So 0089, that's hexadecimal. So can we just like put this in and have it be automatically recognized as a hexadecimal? Yes, it does automatically get recognized as a hexadecimal. Wait, so if we do... If we do that... Ooh, okay. And if we do 169 and then the character of that. Ooh, okay. That's cool. How does hexadecimal work again? Ah, okay, okay. So if we don't want 169 and we just want to print this thing out, basically, we just have to do that, right? So it prints A9. Wait a minute. Ooh, okay. Okay. So if I do that, just don't change anything, right? Nice. Okay. So I have a even if yeah, Bengali Ishar. So I can print a Unicode. I can print its character, and I can also print what it means as a number. Cool. And then if I have a number like that, then I can print what it is. I have to make a new line. So I have a number 9351, and I tried to turn it into a hexadecimal, and this is what I got, 2487 as a hexadecimal. So let's... Oh, wait, no. 2554, right? So if I put 2554 back in here, we should get the same character. Nice. Except, yeah, we should do %04 and OX here just to be standard. Yep. Cool. Very, very cool. Okay. Right, I got it now. Let's keep going. It's fun to play with around for a bit. Hmm. Right, so what exactly does this do? Bengali letter. Okay. I always thought you had to um just specify like Bengali again since you're asking it to print the variable twice. But I guess it doesn't really matter. Could you just like use what is it? Okay. Wait a minute. Does it have to be that? Could you use this instead? Or will it just not work? Yeah. You have to use that to make it be interpreted as a... Okay. Okay, interesting. Manipulating characters with Caesar's cipher. One effective method of sending secret messages in the 2nd century was to shift every letter so A becomes D, B becomes E, and so on. The result might pass for a foreign language. Turns out that manipulating characters as numeric values is really easy with computers, as shown in the following listing. Say we don't do double quotes because that's a string. But then, what if we put like 2 letters in here? This doesn't work because, yeah. But then I remember we had like this thing, right? Oh, it's backtick. Okay, that's a different thing. It's single quote. So a backtick would work. Yeah, okay. Right. Okay, so that prints D, but if we have Z, yeah, okay. Huh, okay. Rot 13, 20th century variant of Caesar cipher. It has one difference, it adds 13 instead of 3. Rot 13, ciphering and deciphering are the same convenient operation. Okay. ¿Cómo estás? So this prints 15 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's because, okay, I see ish the issue. Range keyword. Okay, let's try this out, see what it does. What does it actually do? Why is there 0 and then suddenly a 2? Hmm. Oh, the index. But we missed. Where's the 1? If this is the index, then where's the 1? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We got 14 here, which means we skipped. Yeah, we skipped 4 as well. That's because it took up like more than. Huh, okay. Hmm. Okay. Invalid character. Oh, it used a different type of, yeah. Right, so we don't really need. So we want to preserve. So this will add 13 to the blank spaces, which we do not want. So let's give it a go and see what happens. Let's not do that. Huh. Mm, Hmm. One, two, three, four, five, six, seven. Huh. Because now there's capital, so I don't know how to deal with the capital. Unless you want to make a, unless you want to make a case for each of these. We could, yeah, right. This down, but then, yeah, we would only be manipulating lowercase letters and not the letters with the ticks in them. Just, but whatever. Let's just see what happens if we. Minus 26. Oh, okay. I see. Now we could add, yeah, another one. And this will deal with the capital letters. But then that doesn't deal with the ticks. Do we need to deal with the ticks? Characters with accents are preserved. Oh, letters with accents are or punctuation are unchanged. Alright, let's see if our message, if our rot13 function here is indeed correct. So you should get habin pozb rivgaf. Oh, habin. Wait, the H didn't get changed. That's a bit weird. Oh, why do we have a double? Why do we have a double? Okay. Ubin pozb rivgaf. Ubin PBZB. P. It contradicted itself. It said that letters with um punctuation are unchanged. Yeah, ChatGPT kind of sucks and makes mistakes like that. So I think this should be correct. So that's okay. Let's do lesson 10 now. How long have we been streaming? It's been about 2 hours now. Maybe I won't do the fucking, what was it? Capstone. I'll just read through it and like think about it and then actually write the program some other time. But yeah, let's look at converting between types. Okay, type conversion. say I turn age into a float, and then you can do these calculations, turning it into an int, yada yada yada. Convert types with caution. In 1996, the unmanned Ariane 5 rocket veered off its flight path, broke up, and exploded just 40 seconds after launch. The reported cause was a type conversion error from a float 64 to an int 16. Bruh. With a value that exceeds 32,767, the maximum value an int 16 can hold. The unhandled failure left the flight control system without orientation data, causing it to veer off course, break apart, and ultimately self-destruct. Dude, so much money wasted. We haven't seen the Ariane 5 code, nor are we rocket scientists, but let's look at how Go handles the same type conversion. If the value is in range, as in the following listing, no problem. Right, so if a float 64, we turn it into an int 16, and it's basically just the same thing. If the value is 32,768, which is too big for an int 16, the result is that we've come to expect of integers in Go. It wraps around, becoming the lowest possible number for an int 16, negative 32768. The ADA language used for Ariane 5 behaves differently. The type conversion from float 64 to int 16 with an out-of-range value caused a software exception. According to the report, this particular calculation was only meaningful prior to liftoff. So Go's approach may have been better in this instance, but usually it's best to avoid incorrect data. To detect whether converting a type to int 16 will result in an invalid value, the math package provides min and max constraints. Oh, so math.min int 16 will print like negative 3,000, 32,000 something, and max int 16 will print 32,768. So yeah, we could try that out, like right now. It's not uppercase. So print fmt.println math.min int 16. We'll do max. So max should be 32,768. 32,767. Well, okay, yeah. Basically. Okay, cool. Okay. String conversions, right? So a rune can be converted to a string. Let's try this. Var pi rune print pi fmt dot print right. So if you convert it to a string, does that turn into pi? Yes, it does. Cool. Okay. To convert digits to a string, each digit must be converted to a code point starting at 48 for the 0 character through 57 for the 9 character. Thankfully, the itoa function in the strconv package does this for you. Ooh, okay. Huh. Bro. Is this even in... Will this even be in the database? It's searching. The fuck are these, some of these symbols, man? See, that worked instantly. Our replacement character. I guess that just means like this character, this number that you put in is kind of like invalid. That's plus 8314. Superscript plus sign. So I guess is the idea, so hex to int. So yeah, so 8314 is okay. I see, I see, I see. Okay. So I can't just put like a 10 there and have that be converted into a string. Yeah, it'll just be nothing. So I need the strconv and then itoa, and that'll turn the number into a string. And then atoi will turn ASCII into an integer. Ugh. Mm-hmm. Oh. Ugh. Okay. Capstone. Let's go. We are like a quarter of the way through the book. And we'll get to unit 3. You will write a program to decipher text using a keyword. Before describing the Vigenère cipher, allow us to reframe the Caesar cipher, which you've already worked with. With the Caesar cipher, a plain text message is ciphered by shifting each letter ahead by 3. The direction is reversed. To decipher the resulting message, assign each English letter a numeric value where... Okay. Ugh. Decipher the text in table 11.1. Start with the letter L and shift it by D because L equals 11 and D equals 3. The result of 11 minus 3 is 8, or the letter I. Should you need to decipher the letter A, it should wrap around to become X. Decipher.go. Write a program to decipher text shown in table 11.2. To keep it simple, all characters are uppercase English for both the text and keyword. Okay, that would be very helpful. The string.repeat function may come in handy. Give it a try, but also complete this exercise without importing any packages other than fmt to print the deciphered message. Try this exercise using range in a loop and again without it. Remember that the range keyword splits a string into runes, whereas an index-like keyword 0 results in a byte. You can only perform operations on values of the same type, but you can convert one type to the other. To wrap around at the edges of the alphabet, the Caesar's exercise made use of a comparison. Solve this exercise without any if statements by using modulus. Okay. I will think about how to implement this. What does strings.replace do exactly? Ooh, okay. Interesting. Strings, blah, blah, blah. Wait, UTF-16 presentation. The UTF and there's so many UTF-8 encodings I don't really understand. Do they all convert to the same hex number? 240, 240, 157, 132, and 158. Oh, there's two UTF-16 encodings for this. 55348 and 56606. So let's say I do, yeah, 56606. What does that print out? Nothing. What about 55348? Nothing as well? What about the hex? Nothing as well? See, sometimes this makes sense, sometimes it just doesn't. That character is... So, OXFO. Right, but this doesn't work. What? What the heck? Okay, if that doesn't work, then 119070. A missing hex code? Oh, I think it's too. Yeah, it can't fit in the UTF-16, so it needs a UTF-32, I think. Oh, it's not. Oh my god, I'm so dumb. It's not. It's different UTF-8 encodings. It's. That's so dumb. Okay. It's two consecutive things. Okay. So if I do like that. Okay. Wait. Does this make sense? 55348. Oh, I don't. Huh. Okay. I could use percent %U, capital U. Nope, doesn't work. Capital X. Capital X doesn't work. Still nothing. Still nothing. Do I have to put text twice? Oh my god. So dumb. But I remember we didn't have to do it before. Okay. I think, yeah, sure. Cool. I'll see you next time. Bye.